don't like the cameos that you got on the news.
Oh, that's scary. I'm looking, I go, that's scary man on the TV. As I was preparing the lesson today, it occurred to me that I had to call a couple of quick audibles here. So bless you, before we actually get into evaluating the harder logarithms today, there's a little bit of a back lesson that we have to do here. It shouldn't take more than about 10 minutes, but I numbered them as if to say, hey, dude, do this one first. So the first thing we have to talk about is something that I feel like I hit it in Algebra 1. I just don't remember ever the extent to which I do. So let's talk about this. Are you guys aware that that is a fact? That's okay. Just say no. Right. Okay, good. That's what I need to know. I need that feedback. I thrive on that feedback. So the thing about square roots and exponents is you can interchange between the two, and your ability to do this will be critical to your success on this next section. So I need to be able to look at a root of any type and be able then to convert it from a root or a radical into an exponential. Now, you might wonder, where did the numbers 1 and 2 come from? Well, let me just show you real quick. The number 1 came from right there on the x. X doesn't have an exponent, but if something doesn't have an exponent, we've always known that, well, it does. This is a 1, right? And then the 2 comes from the fact that this is a second root, which again, you can't see either of those numbers. So you're at a little bit of a disadvantage here, because when someone puts that red radical sign and they don't put a number outside, then we assume that it's a second root called a square root, right? So the numbers 1 and 2 will always specifically come from the power of the thing inside the radicand. It'll always come from there. And the bottom number on the fractional exponent will always come from the index of the root. So having said that, if that made even an ounce of sense, I should be able to put something like this up here. And you should be able to convert it to exponential. What will it be? X to the power of 2/5. The base is still staying as x, right? The thing inside, it's just that we're manipulating it and converting it from radical form to exponential. Radical form, exponential. Let's go again. The 4th root of m to the 10th. What's that going to be? And again, stop just saying fractions to me, okay? It's really important that you not do that. I appreciate where you're coming from, but just saying 5/2 is massively incomplete. What is the actual conversion? M to the power of 5/2. Good. Okay, we can't just ignore the fact that there's a base there. So that guy, M or X or whatever's inside, he stays part of the process. It's just that we're converting it. We're converting it from a radical form, we say, to exponential. This one, I think, is, I'm going to put the answer up here. Actually, I'm going to give you and I'm going to, over here in red, I'm actually going to write the answer. And I know that looks like, oh, what has Mr. Ahern been hitting the sauce? No, that's the answer. Can you guys maybe collectively try to figure out where such a nonsensically odd answer would come from? This skill that I'm about to show you will again be a pivotal, a critical sort of skill. So yeah, I mean, I don't, if I were you, like when I was 17, taking this class from Mr. Brown at Smoky Hill High School in Aurora, Colorado, someone put that up on the board, I'd have been like, yeah, I don't know what you're talking about. Just go ahead and show me. So here's the deal. What I did is I took the number 32 and I rewrote it as 2 to the 5th. This one ability will pretty much differentiate your successful versus non-successfuls here. So why did I do that? Well, I did that because I could, quite frankly. And there are going to be more reasons why we do things like that in the coming 20 minutes. But for now, I did it because, well, I could. And I wrote 32 is 2 to the fifth. And then as you can see, knowing what you've seen from the last 3 or 4 minutes, that is the same as what? 2 to the 5/10, which then, of course, I reduced to be 2 to the 1. Does that make any sense at all? Okay, let's go again. Let's do the fourth root of 25. What is 25? It's something. It's 5 squared, right? Having said that, what is the simplified or converted version of this expression? 5 to the 1/2. Yeah, it's not a mixed number, not 5 1/2. Right. Got it? Any questions about that particular idea? The main takeaway from that, there was a couple. I mean, the basic takeaway is just for God's sake, know that these two numbers that I'm circling pretty boldly in yellow here, those are the guys that are going to create the exponent of your converted expression. But also know that there are going to be instances, and I'll guide you through this, in which you want to take this number on the inside and write it as a power. And if there are options, like let's say I did this, no, don't do that. That's a bad one. Let's do the 8th root of 64. Can anyone think of a dilemma? If you're a super mathy person, if you were trying to follow along with the two examples above it, you should hit a wall. What's the dilemma with the number 64? Okay, fair enough. So 64 is 8 squared. But what else is 64? It's also 4 to the third. What else is 64? It's also 2 to the sixth. And so if I'm any good at this job here that I do, when I'm done with this lesson, you'll understand that there will be guidance in the problems themselves that will cue you as to which of those you ought to take. Oftentimes, you won't have options, but if you do, the other parts of the problem, the stuff you're going to learn today, will give you the guiding light and say, you should pick this one for reasons you'll soon understand. Got it? So if I gave you this problem on the board, the most simplified version, just FYI, if this was all you had to go on, the most simplified is going to be the one with uh, the lowest base. So if this was all I had to go on, the quote unquote best I could do would be to call it the 8th root of 2 to the 6th. It's just like I said, if this was all you had to go on, but there will be other reasons when we might not choose this route. And so this one would wind up being 2 to the 3/4. Got it? So that's introductory section number 1. Make sure you're good at it. All right. Introductory section number 2 is evaluate that log. We learned this yesterday. Hurry up, go. What is it? So let's talk about what we learned yesterday. If I gave you like log base 4 of 64, what would you say it is? Yeah, I can tell if you've done your work. If you say 3, I know you did your homework. How about log base 5 of 25? What's that? Good. So those are evaluatable to us because we understand that cycle. We understand that water cycle thing, that this to the power of the unknown number has to equal this. Or in the second problem, that this to the power of the unknown number has to equal this, right? It's that cycle that we get used to seeing. What's missing from this problem up above? What's missing? The base. Good. So I have a few objectives for this little portion of the lesson, and one of them is to teach you this type of logarithm. You're going to see a lot of these is called a common log. You 100% need to know this. This is huge. We're like prioritizing, put this high. A common log is what's very common, I guess, and it's what we call a base 10 log. It's the most common type of logarithm just because we work in a base 10 number system, right? Your entire number system, our entire number system that you've ever used, that humans have ever used, is predicated on the fact that we have 10 fingers, which if you really stop and think about it, it's actually pretty cool. Like humans, whatever you believe in, creation or evolution, humans have 10 fingers, right? You agree? And so the fact that we use a number system that relies on 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, is not coincidental to the fact that we, as in older days, counted on our fingers, right? So, sorry, Seth. That's very, very insensitive of me. Anyone watching this recording is going to be like, what just happened? And we're just going to keep that between us. All right. No one will ever know except us. I'm really sorry about that. So anyways, our number system is predicated on tens. Like when you move a decimal place, you multiply by 10 or divide by 10. Like that's why the rest of the world has numbers figured out, and Americans are still stubbornly ignorant to the fact that the metric system is what we should all use, right? Because it's based on tens. But anyways, when you see a logarithm and you don't see a base, if it says log without a base, it is a base 10 log. So what is log of 1,000? 3. It is 3. Because even though I know that I can't see the base, I know from what I just learned that it is actually a base 10 log. And 10 to the third equals 1,000. Got it? All right, let's practice another common log. What is log of 1/10? Good job, Seth. So remember, it's a base 10 log. I'm just writing them in because this is new to us, so those little red numbers, but usually you're just not going to see them. And so 10 to the power of -1, of course, is what would cause it to flip down and become a 1/10. Everybody clear on what's going on there? Okay, so that's called a common log. The other type of logarithm, and I'm going to show you a video someday. I'm not going to make a promise as to when it's going to be. Make sure you guys watch the end of you watch the end of this, okay? You don't want to miss it. I mean, not like it's going to be exciting. You don't want to get behind. So the other type of logarithm is this. Yeah, it's this. And what's happening on the TV is way more important than someone walking out the door, right? So there you go. This is something called a And once I show you a video on the number E, I know it's a letter, but it's a number. You guys know pi, right? Pi. So you know how pi occurs? Does anyone know how you can always make a pie? Like, no, don't be smart, like with the oven and stuff, but like, do you know where the number pi comes from? Radius or almost. It's if you take any circle, like if you go home tonight and you measure the distance around one of your dinner plates, like if your mom has one of those like cloth, like sewing rulers, I don't know what you call those, like a measuring tape or something. There's probably a name for that. If you measure the circumference of a circular dinner plate and then measure the whole distance across, called the diameter, if you divide the distance around by the distance across, regardless of the size of the circle, it'll always be pi. So the number pi isn't something that someone created. It's just a number that occurs naturally in mathematics. The same can be said for the number E. E is a number that is naturally occurring. If you should have an E button on your calculator for the record. And if you hit the E button, it'll say like 2.71828, something like that. So let me go and Google this real quick and I'll just show you. Yeah, don't do the 2 capital E's. That's scientific notation.
Yeah. You have like something like 2.67 times 10 to the 6. Or like 10 to the 13.
So this right here is an approximated version of E. And so if you hit, oh, come on, man, use a mouse. If you hit E on your calculator and just hit enter, remember, make sure it's the lowercase e, it'll give you this, only less digits, obviously. Your calculator doesn't have that much room on it, but this, much like pi, is a number that occurs naturally. And if I go into that with you today, then we're not going to get anything else done. So just that day is coming when we're going to talk about like the natural discovery or whatever of the number E. But just know that for now, E is a letter that represents a number, much like pi is a symbol or a Greek letter that represents a number. So this is E, it's 2.71828, blah, 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 on and on. So having said that, a natural logarithm, when you see ln, is specifically a log with a base of E. So if I say to you, what's the natural log of E? I'm asking you, what's log base E of E, and what is the answer? Bless you. Try again. Try again. Then, yes, of course it would just be 1. If I asked you, what's log base triangle of triangle, what's the answer? 1. If I said, what's log base happy face of happy face, what's the answer? It's 1. You understand the ridiculous nature of these questions is that I'm asking you, what power do I have to raise E up to get it to become E? And the answer is, of course, 1. If the base and the argument of a log are the same, then the logarithm has to be 1, right? I could put log base Kleenex of Kleenex, and the answer is 1, right? We clear? All right. How about this one? Nope. This is where things could potentially get a little tricky before we get to the actual trick. What happens a lot of times with natural logs is we forget that we actually have to write them out to make it make sense. So let me I'll do a courtesy to you here, and I'll write this out as log base E of E to the 10th. And once this clicks, you'll realize it's one of the most ridiculous math questions I've ever asked you. Corbin, are you sleeping? You looked like you were sleeping. Were you sleeping? Okay, good. I heard someone say it, but I'm just hearing one voice say it obviously isn't satisfactory. So let me show you the situation that we're in, and you'll realize how silly it actually is. I'm asking you, E to what power equals E to the 10th? I mean, think about the ridiculous nature of this. What has to go right here? It has to be 10. It just solves itself. It answers itself. I'm asking you, hey, what exponent would I have to put on E to make it say E to the 10th? You're like, are you messing with me? 10. That's what it is. How about this one? How about log base x of x to the 4th? The answer is 4. Again, it's so hilariously simple that it can actually be confusing. Okay? So the main purpose of this portion of the lesson was really to get you familiarized with this notation. When you don't see a base, what is the base? It is 10. When you see log without a base, it is 10. And when you see this, it is what? It is a log with a base of E. Are we clear? Okay, then let's head on to what we're actually doing today. So you need to have that background knowledge or none of this will go well. So I have all of this numbered. I have at least the first 5 placed in order. So actually we've already done that one and we've already done that one. So that puts us on to this one. Say again? Well, I can't hear you. It's a half, correct. Now let's talk about why that is. So one of the things we learned very first off out of the gate today was that anything with a radical on it, any form of root, square root, cube root, fourth root, can and often should be written using exponents. And so if I took this portion right here and I rewrote it using exponents, what would it actually say? What is the square root of 8? You'll have to get this into your heads quickly. We don't know what the square root of 8 is, but what it is 8 to the power of 1/2. And what happens now is it becomes that ridiculously simple situation that we talked about in the last couple of problems, where again, you think I'm probably just trolling you. Like, are you seriously asking me what exponent I have to put on 8 to make it say 8 to the 1/2? And the answer is, well, yes, obviously 1/2. The key to that, the success step there is, do you know how to turn something with a root into something that has an exponent instead? And that way there we can apply generally pretty common sense to it. How about this one? I'm going to give you another one that's similar to that. I'm kind of calling an audible on myself here. I just want to make sure that everybody is good before I press to the next one. Log base 7 of the 4th root of 7. It is 1/4. Very good. And for anyone who might not know and is the kind of person that doesn't like to ask, here it is. I take this quantity right here in this red box and I rewrite it as what it should be. I need it identified as something else. I need it as 7 to the power of 1/4. That goes back to the first thing we learned today. And as soon as I see that, I go, oh, yeah, this is one of those deals where this guy and this guy are the same. So my answer is just the exponent, right? So far, so good. All right, we're going to step it up a notch now. So I told you earlier that there would be some clues along the way. And Your Honor, I present Exhibit A, which is now I've got clues. So if you've been paying attention, you know that 64 can be written in multiple ways, exponentially speaking. It could be 8 to the 2nd. It could be 4 to the 3rd. And it could be 2 to the 6th. If anything that I've just said makes sense, you should know which of those three we want to pick. Which one? 4 to the 3rd. And I want 4 to the 3rd because I want the base 4 to match the base of my logarithm so that I can shortcut and get the best, quickest answer possible. So I'm going to take the number inside the 64 and I'm going to rewrite it as 4 to the 3rd. And then what I'm going to do is I'm going to follow my own instructions and I'm going to rewrite this quantity in this red box as something that does not have a root on it, but rather an exponent. So I'm going to rewrite this whole math problem as log base 4 of 4 to the 3/5 power. See how it's all coming together? What is the answer then? Good. Any questions on that? Okay. On to the last part then. Sorry, I've got to scroll. If you're still writing, hustle up, okay? Because I got to change screens now. You good? All right. I'm going to show you a new strategy. You should actually draw like a line in your notes right above this, just because what I'm about to teach you below this line is a super handy skill that will often bail you out of a confusing situation. So that purple line is like a marker that says, okay, below here, I'm going to show you the most powerful strategy to do this that I personally know of. If you didn't know what you're up against right now, you'd look at this and say, this is not fair. Like if you gave me log base 2 of 8, I'm like, well, that's 3. This is not that situation. This is saying 8 to what power equals 2. And I go, well, that could be really confusing. And if you really know your conversions, you probably already know what the answer to this one is. But here is my strategy. I hope you're still awake. And if by chance you're, nodded off, and you should fully wake back up and take this. Your power strategy from now on is to put an equal sign and put an X. This is going to carry you through so many problems. If you haven't done that, do it right now. Put equals x in there. Now what we're going to do is we're going to embrace that water cycle. I think I talked about it yesterday. And we're going to take this and we're going to cycle it out. We're about to convert it from logarithmic to exponential. So what I'm going to do is I'm going to just take the three players in the game and I'm going to build an equation out of them. You would agree that this to the power of this by default must equal this, right? You see that little water cycle diagram going on? Get used to it. So what that's going to say if I write it out exponentially is actually, oh, so you mean 8 to the power of x equals 2? Correct. Now, the only thing left for me at this point to do is make my bases the same. And thank goodness we've got good basic skills because my bases are 8 and 2. And what I need to know is, can I make them both into quantities of the same base? What is 8? What is 8? Sue said 2 to the third. Bless your heart. 8 is 2 to the third. Now, I'm going to do something here, and it's always like when you see something done the first time, you kind of go, why? And then I hope it clicks. This is why. I'm going to take this number in the green box, and I'm very strategically going to write it as what Christian said. I'm going to rewrite it as 2 to the third. Now, the reason I've done that is because the bases are now the same. This is, if anything's going to get you today, it's going to be this. And I've got 4 more examples of this with more if you want them. So here's the deal. This is a fact. If I told you that 2 to the power of 3x is the same as 2 to the power of 1, big leap here, what could you tell me? What has to be true? Don't tell me what x equals. Just tell me, generally speaking, what has to be true. Those two what? Well, of course the bases are equal. I mean, 2 equals 2, for God's sake. Listen, yes, if you have two expressions that have the same bases and they're equal to each other, you could argue this till you're blue in the face. The bottom line is this: the exponents literally have to be the same as each other, or this could carry no water, right?
Yep.
Having said that, what I can do now is cancel out the bases and write a little 6th grade equation and say, wait, so that exponent has to equal that exponent? Right. And just like that, divide both sides by 3. What does x equal? And there's your answer. The key is to make the bases the same. Let's try again. Log base 64 of 32. What's my power strategy? What am I going to do first? Put equals x. And now we're going to water cycle this up and out. So we're going to take this to the this equals this. You're going to literally write out the result of those purple arrows as an exponential equation. So let me get this straight. 64 to the power of x must equal 32. So I ask you this. These two yellow numbers, 64 and 32, they're both powers of the same number, right? What? I might, if I sat in this room as a teenager, I might have said 8. But here's the deal. Yeah, 64 can be written as 8 squared, whoop-de-doo. The trouble is 32 cannot be written as a power of 8. So 8 is out. What else are they both powers of? Powers, exponents, 2. 64 is specifically 2 to the power of 6. And 32 is specifically 2 to the power of 5. Having said that, we can come to a consensus, an agreement, that if I take this number, 64, I can rewrite it as 2 to the 6th and then continue and raise that on up to his original power of x. I can also take this number in the red box and I can rewrite him as 2 to the 5th. We agree. There's all sorts of ways. When you guys were saying things like 16, that bothers me. We're talking about exponents here. 16 to some power is not 32. Are we clear? So when we talk about powers, we're talking not basic multiplication here. The powers mean exponents. Now, if 2 to the power of 6x equals 2 to the power of 5, what has to be true? 6x has to equal 5. Therefore, what is x? Done. Okay. You could offer me money to come up with a better way to do that, and I could not. I would say, take your money. I can't. This is the most clean, and biased, obviously, but put an x in there, water cycle it out, make the bases the same. Done. Let's go again. Needs to know you can answer this question. What is step 1? Thank you. There it is. Next step. Water cycle that sucker. Take this to the this equals this, just like that. What's that going to say? Beautiful. And now again, I go off to the side and I say, what is something that is a base that I can use to make both of those? So we agree that 125 is 5 to the 3rd. And we agree that 25 is 5 to the 2th, right? So I take my 5 to the 3rd, just give it its old exponent back. And if 5 to the power of 3x equals 5 to the power of 2, what is true? 3x has to equal 2. If the bases are equivalent with exponents, the exponents have to be equivalent. And then I divide and I get x equals 2/3. Is that clicking? Fantastic. First step. Next step. What's it going to say after we hit it with the water cycle? Gorgeous. And of 9 will not work because 27 is not a power of 9. So again, when we have options that, like I told you earlier, the options will be taken away out of necessity. Like there's going to be a best choice. And so in this case, 3 works for both. So I look at 81 and I'm like, hey, I know you. You're 3 to the 4th. If you don't know that, you're going to want to probably get good, noob. Like start learning those dang things. Learn your powers, right? You want them to be quick. Like you don't want to be held back by that. So 81 is 3 to the 4th. And then we're going to reapply his original power of x. 27 is 3 to the 3rd. And what has to be true at this point in time? 4x has to equal 3. And if 4x equals 3, then x equals 3/4. I have one more for you, and I can do more if you'd like. It's up to you. You guys getting this okay? Would we agree it's significantly more difficult than yesterday, but as typically has been the case all year, not causing you guys much stress? Good. Probably do a couple more, actually. I just occurred to me I should I'm going to add on to my note card here. I'm going to add a couple more of these. I don't know why I put this on there like it was just no big deal. So, step one. Yeah, that's just not even really up for discussion at this point. Step two.
And
Yeah, good. I would think that if you don't do either of those two steps, you're just asking for trouble. Like those aren't do them because my teacher said to do them. Those are just do them because I need the equation to look a certain way. So now we're thinking about those numbers and what are they both powers of? They are. They're both powers of 2. So if I take the number 16, I recognize him as what? 2 to the 4th. Yeah, 2 to the 3rd is 8. So 2 to the 4th, and then I reapply his original exponent of x. And this is a good test of how much did you learn yesterday. What is 1/8? Nope. It can't be. It's 2 to the something. It's 2 to the negative 3rd. Remember what we learned yesterday is that if you have a fraction, you can only get that by giving something a whole number has to have a negative exponent to get it to flip-flop down like that. Okay, so it's still a 2, it just has a negative exponent to make it work. And if these two things equal each other, then it's a fact that that must equal that. Purple must equal purple. It's a fact. So if 4x has to equal negative 3, what does x equal? Nice. All right. Let's do at least one more of those and then we'll be done for the day. And then tomorrow will be a nice big old chunky work day for you, okay? Let's do log base 27 of 1 over 243. If someone were to walk up to my desk and say, I need help with this, I would of course say, did you do the first 2 steps? Well, no, there's nothing to get in the first 2 steps, right? Step 1 is just to do that. And then step 2 is just to water cycle it out, 27 to the power of x. There's nothing to understand about that. That's just following robotic instructions. At this point now, you got to know some stuff about some stuff. You got to have that number sense. What are 27 and 1 over 243 both powers of? They are. Again, it's really beneficial to know information that might otherwise seem useless. Like 3 to the 3rd is 27, right? And 3 to the 4th is 81, which turns out we don't need that one. But the kicker is the guy after him. What's 3 to the 5th? It's 243. The quicker you come to just memorize stuff like that, it's going to be quicker. So now we've recognized our guy. 3, you're our dude. So I'm going to take the left-hand side, 27, and I'm going to say, you, sir, I'm going to write you as 3 to the 3rd. And then I'm going to reapply your original power of x. And then I'm going to take green box over here. Good job, Tristan. He is 3 to the negative 5th. We require that negative exponent to get the flip down. And at this point, all the work is done. All that's left is a little 7th, 6th grade equation. 3x must equal negative 5. Therefore, x must equal negative 5/3. Got it? If by reduce you mean convert it to a mixed number, my answer would be don't bother. No one likes mixed numbers. Actually, some people do. We call them sociopaths. So, yeah. You guys got it all? You know what? The assignment will be on Delta, but I think I'm probably going to just take it off and I'll reassign it tomorrow morning just because. I figured that'd take a while. I didn't know it would take 52 minutes a while, but there you go.